Hello, this is Professor Jim Caffey, and welcome back. Today we're going to do Chapter 17 on analyzing starlight. So the next few chapters talk about stars other than the sun and how we analyze the light we see from them. Well, stars can have different colors, and colors talk about temperatures with stars. So a red star is very cool. Those are some of the stars that I work with. And some stars are blue and white, and they are very hot. The sun is a yellow star. We talk about magnitudes, and there are two kinds when we talk about brightnesses of objects in the sky. Apparent magnitude is what we see. How bright is it? The sun is the brightest thing in the sky, the way we apparently see it. A full moon is a lot fainter, and then we see limits as to how faint a telescope can go. A 1 meter telescope is about 19th magnitude. For comparison, the faintest stars you can see with your eyes is about 5th, maybe 6th magnitude. And we go all the way down to our Hubble telescope, you can see 30th magnitude. Now, in astronomy, we deal with some extremes numbers. And so the difference between the sun being bright and what we can see as the faintest things in the sky is really about a 10 billion fold difference in brightness. Here is a star cloud from the Hubble Space Telescope looking towards the center of the Milky Way galaxy, and you can see the different star colors in that crowded field. William and Margaret Huggins were the first to identify the lines in a spectrum of a star other than the sun. So what they did was they analyzed the chemical composition of another star. Based on the temperature of the star, we will find features in that spectrum for each temperature. This is a full spectrum of all the stars, and we see these dark lines in the rainbow of the spectrum. So what a spectrum is we take a prism or we take a diffraction grating cut with a laser, and it splits white light up into a rainbow. We see many dark lines. These are absorption lines where elements in the sun are absorbing that energy, and those dark lines is where that element has been absorbed and the sun is not emitting it as it should. We can tell what a star is made up of and how hot it is based on its spectrum. Annie Jump Cannon was very well known for her classifications of stellar spectra. Many of the advances made in astronomy around 1900 were from many well-equipped women. Brown dwarfs are not quite stars. They don't have enough pressure and heat to kick on thermonuclear fusion. So it's kind of a failed star, brown dwarf. To be a star, you have to have 8% the mass of the sun or so. More information about spectral lines. In the blue, we get the ultraviolet. We can see between 400 and 700 nanometers with our eyes, and then past 700 is the infrared. Now, if a star is moving towards us, then that is called a blue shift. The lines in the rainbow spectrum, continuous spectrum, will shift towards the blue. That means it is coming towards me. Whereas a star or object or a galaxy moving fast away from me, the lines are shifted towards the red. So think of a slinky, toy slinky. If you stretch it out, the links get longer. That's a redshift. Longer wavelengths and sounds are redshifted. If you hear an ambulance or a police car going away from you, you will hear a siren that gets lower in pitch. So I like to do this. It sounds like this. As it goes away, it's going to get fainter and lower in pitch. As it comes toward you, it gets higher in pitch and louder, so it sounds like woo wee 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 as it goes by you, and then changes as it goes past you. So those are red shifts and blue shifts. Some stars that are nearby have a large amount of motion that we can photograph. We call that motion proper motion. It is a sidewards motion in the sky. We cannot tell proper motion coming towards or away from us. Barnard's star was a famous type of star like that. The Big Dipper has changed in position over the years. The stars, they appear to form a Big Dipper, but they are actually different distances away as we see them in space. So 50,000 years ago, it didn't look like much of a dipper, and in 50,000 years, it will look like a wheelbarrow, maybe. We can also use a spectrum to tell if a star is rotating. Because if a star is rotating, then we can see one side coming towards us. Remember, that's what kind of shift is that? That is a blue shift. If it's coming towards me, and that slinky gets smaller. As that object goes away from me, we get a red shift. So as a star rotates, you have one side coming towards you, and you can measure that. It's small, but you can measure it. The side going away from you, you can measure that. And we can measure how fast the sun or any other object rotates. The sun rotates in about a month, 4 weeks or so. It doesn't rotate like a solid body, so it's different depending on where you are on the sun. The rotational period of the star Altair is 6.5 hours. Henry Draper and James Lick here, very famous astronomers. Draper has a catalog of stars next to his telescope for photography, and his work continued on. Lick was a philanthropist who funded astronomy work. That's going to do it for chapter 17 on analyzing starlight. I thank you for joining me, and see you next time for chapter 18.